Hey guys, how you doing? So this is the crash course for the physics component. Now, I mentioned to you guys, particularly to my class anyway, that I was going to try my best to make a video for the revision of the exam. And I know this is probably running a little bit late, but I just thought you guys might appreciate this really quick crash course on the physics component. Hopefully this will explain some things that you're not sure about. It probably won't cover everything, but it might get you guys going on clearing up some of the things that you're not sure about during that study process. And it might help you guys with that. Now, I've decided to go for a bit of a different approach because there's going to be a bit of graph drawing in that. So what I've just done is I basically face my computer against a whiteboard, and I'm going to try my best to work off the whiteboard and have you guys sort of follow along with that. So I'm not really going to use the PowerPoint. I'm just going to go off some of the main kind of key ideas that we want to cover. And just help you guys with the graph drawing and the working out and things like that. Okay, so I've never actually done this before, so it's probably gonna look a little bit rusty. I've just found a little old whiteboard lying around, gotten some pens and just gotten it together. So we'll see how we go there. Okay, so we're gonna start looking at some of the topics. Now, the main topics that we're gonna really just cover in this video is looking at speed, looking at velocity, and then acceleration, and then we're going to look at the distance time graph and velocity time graphs, and then trying to work through how to read those graphs as well. Okay, so before I start, I've just sort of put all of the formulas that are on that you probably should make an attempt to try and remember. I've put it on there, and what you've got is the speed graph, the velocity and the acceleration, and then all the derivatives and broken parts to it. Alright, so let me just go through that with you guys. You're probably not going to see my face for most of the lessons, since I'm going to mainly use my hands to try and show you guys what's happening here. Okay, so let me go through the formulas with you guys. The first one is the speed formula. So speed is equal to distance over time. Yeah, you can rearrange those formulas so that you can get distance is equal to speed times time, or time is equal to distance divided by speed, right? And these formulas all mean the same thing, but they're just obviously isolated, so you can work out speed with this formula. If you want to work out distance, you use the middle formula. If you want to work out time, you use the last formula. Okay. The next set of formulas that you've got there is the velocity ones. Now, velocity being v instead of s is equal to x for displacement, and then t is time, and so you've got a different set of formulas, but very similar in structure. You notice between these three sets here, right? Velocity is pretty much like speed, right? Except it uses displacement instead of distance covered, and I'll explain the difference between those two in a second. Okay, if you want to calculate displacement with the velocity time formula, it will just be velocity times time, and if you want to calculate time, it'll be displacement divided by velocity. Okay, the last formula that we are going to go through is the acceleration formula. So acceleration is equal to velocity divided by time. That can also be interpreted as speed over time as well, but we'll go through why it's not speed in a second. Okay, and of the acceleration formulas, you've got your kind of four main derivatives. Now, the key thing to note here is this v here is not the same as this v here. This v here just means velocity in general. This one means final speed, okay, or final velocity. Final velocity is what the object is at the end of that particular time frame, and then the u is initial velocity, and then time is there. Okay, and then once again, you can rearrange these formulas so that you can have final velocity is equal to initial velocity plus acceleration times time. Initial velocity is equal to final velocity minus acceleration times time, or time is equal to final velocity minus initial velocity divided by acceleration. Okay. The final thing that I've sort of tacked in there as well, this is something that I've done with my class, it's easy to remember, is the conversion rates between kilometers per hour and meters per second. Okay. So if you have an object's speed or velocity shown to you in kilometers per hour, for example, a car traveling at 70 kilometers per hour, you can convert that to meters per second by following the arrow and just doing the prompts. Yeah. So if you have 70 kilometers per hour, right, then you can do 70 divided by 3.6 to get meters per second. So 70 divided by 3.6 is 19.4, so it will be 19.4 meters per second. If I give you an object moving in meters per second and I want you to convert it into kilometers per hour, you then do the opposite and you multiply it by 3.6. So an object traveling at 10 meters per second will be going at 10 times 3.6, which is 36 kilometers per hour to get the kilometers per hour there. Yeah, and a handy tip that I always remember is that the kilometers per hour unit is always higher than the meters per second equivalent. Okay, so that way you can identify which one's kilometers per hour and which one's in meters per second. Okay, all right, let's get into it. We're gonna first look at speed and velocity, and then we'll move on to some of the other ones. And velocity. Okay. Now we define speed as how fast an object is traveling. Yeah, how fast an object is traveling, and we use distance over time to work that out. Okay. Now one of the key things about speed is that the speed of an object is what we call a scalar quantity. Okay, which means it has magnitude. In other words, it has an amount, but no direction. Yeah, no direction. Yeah, if I tell you an object is moving at 70 kilometers per hour as a speed, it doesn't tell you which direction my object is moving in, and that's what we call a scalar quantity. It has magnitude but no direction. Other scalar quantities include things like weight. Weight will tell you how many kilograms something is, but it doesn't have a direction as to what that object is moving at. Okay, and we work that out using distance divided by time. Okay, so if I was to give you an example of that, yeah, if I say, for example, give you an object that's traveled 900 meters in 30 seconds, okay? You then use the formula S equals D over T to try and work that out. So S equals to distance over time, which is 900 meters divided by 30 seconds, yeah, which will equal to be 30 meters per second. Now, obviously, I've already worked all this out beforehand, but if you follow along, you can do the maths and all that works out. Okay, so my speed here, the object is now moving at a rate of 30 meters every second. In other words, after the first second, it moves 30 meters. After the second second, it would have moved 60 meters, and then after the third second, 90 meters, and so forth and so forth. Okay, and that's what the speed tells us: how fast, how much distance it's covering within that certain time frame. Okay. The difference between speed and velocity really just comes down to that last aspect of direction. Okay, velocity does not track how fast an object's moving. It's tracking its change in location over time. Yeah, so it's change in location over time. Yeah, now this change in location is what we call displacement. So velocity is really displacement over time, or in this particular case we call it x over t. Now what's the difference between distance and displacement, right? If I give you an object that starts here, right, and I say the object has actually traveled in this kind of particular fashion, right, and then it ends up there, right, this is the distance that it is traveling. Yeah, so that's distance. However, if I ask for what its change in location is, you wouldn't say that that's the change in location. Okay, you could say that that there was about 10 meters. However, its change in location is really where it is from where it started, which could be actually only 5 meters, right? And so the displacement would be much lower here because the object has done this kind of windy movement from, oh sorry, that's not distance, that's displacement, okay? Right? It's done this windy movement, but it's ended up only 5 meters away from its original location. And so that's the difference between displacement and distance. So velocity tracks displacement over time, not distance over time, right? If the object is moving in a straight line, however, both values are the same. The distance and the displacement are equivalent, right? If the object just moves straight like that, 5 meters will be both the distance value and the displacement value as well. And you can use the same figure or the formula to work out both. Okay, now the difference between velocity and speed is that velocity with the displacement also tracks the direction that the object is moving in. So velocity is what we call a vector quantity, okay? Right, which means it has magnitude, in other words, an amount, for example, 5 meters per second, 10 meters per second, and direction, yeah? It has the direction that's moving in as well, okay? So if I give you an example, right? So for example, let's go with the same example, yeah? 900 meters in 30 seconds, right? And this time, if I was to show you, let's say the object went 900 meters this way in 30 seconds. 900 meters in 30 seconds, right? from its original location, I can then work it out. I use the same formula here, which are equivalent to the speed and time formula, right? So v is equal to x over t, which equals to 900 meters divided by 30 seconds, which equals to 30 meters per second. However, this time I need to then indicate the directions that the object has moved in. It has moved east or to the right. Yeah, either one will probably work fine in this particular case. Yeah, so that's the difference between speed and velocity, okay? For the most part, however, when we're tracking simple movements like straight line movements, cars moving around, ships, planes, people walking, etc., calculating speed and calculating velocity is largely the same. It's only when we look at things that move in these kind of windy manner or fashion that we then use the difference between speed and velocity a bit more obviously, okay? Now, let's work through a few different arrangements. What if I give you an object's speed and time, and I want you to calculate its distance? Yeah, so let's go with a second example here. Oops, I almost dropped my I think example 2. Yeah, that if we, for example, say had an object traveling at 30 meters per second for 30 seconds, right? And I asked for its distance. Right? If I ask for its distance, you can then try and calculate that by using a different derivative of the same formula. I'm going to use the distance equals to speed times time formula to then work it out. So you go d equals to speed times time, and the speed in this case here is 30 meters per second, right? Times by 30 seconds. Yeah, what I'm saying is that every second it moves at 30 meters per second. After 30 seconds, how far has it moved, right? Which equals to 900 again, yeah, 900 meters, right, in this particular case, yeah. I can do the same thing by giving you the distance and the speed, and then I ask for the time, right, and I'm not going to go through it now, but that would be the general kind of method that you would try and work it out. You can do the same for speed and the same for velocity, right? Now, the key mistake that people often make is not trying to calculate it, but then getting the units right, okay? So sometimes, let's do a combination, yeah? So if I say that, yeah, the object has traveled, let's see, how long would it take to cover 900 meters if it travels at 30 meters per second, okay? Oh, hold on, let me change my units there. Okay, so instead of 900, I'm gonna make up a new unit, right? So, for example, let's go 0.9 kilometers, okay? How long would it take to cover 0.9 kilometers if it travels at 30 meters per second? Now, the kilometers here and the meters are different, so you need to make sure the units are the same. Usually, you would convert down to meters. So the first thing I would do is actually track my distance, 0.9 kilometers, and then convert it into meters, okay? So you can do the maths. 0.9 kilometers is actually the same as 900, so you've got the same scenario as before, but this time I'm using the third equation there. Time is distance divided by speed, so t is equal to the distance, 900 meters. Notice how I'm using the 900 meters and not the 0.9 kilometers, divided by, once again, 30 meters per second. Yeah, so 900 divided by 30 is equal to 30, and the time, seconds, because that's the same unit as my speed there. Okay, so I've got the time of 30 seconds. Same scenario in all three ones, but just rearranged formulas. Okay, so that's looking at speed and velocity in terms of calculating. We're going to move on to the next part, which is looking at how do we recognize a distance time graph and then a speed/velocity time graph. Okay. Okay, let's take a look at this time distance and time graphs versus speed and time graphs. Now, the main purpose of this is being able to look at an object's distance and time, and then being able to sketch the graph and then derive information from it. Okay, so we're going to start with the distance time graphs. Okay, and then we'll move on to the speed and time graphs and see how we go. Okay, now a distance time graph really just puts distance on the y-axis and then time along the x-axis. Now I'm going to make a very simple one just to get the point across, yeah, where distance in meters and then time in seconds, yeah, and you've got 0, 0 there, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 2, 3, 4, 5. Okay, and let's just say, for example, the object has moved in this particular fashion. Okay. Okay, so what I've drawn is just basically a bit of an arch along this kind of way. So you can see the object doesn't quite move as consistently as normal. Okay. What this graph is saying is that you've got an object that is at its starting point, which is 0, 0, and what it's done is it's moved 2 meters away from its original location in the first second, right? 2 meters away in the first second. It moves an additional 3 meters away in the second second, and then it maintains that 3 meter distance away from its starting location for 1 more second, and then what it does is it actually goes backwards and now is 2 meters away in the 4th second, and then it returns back to its original location by the 5th second. So that is the distance that is moved away from its original location versus the time. Okay, so it can be thought of as an object that's going really far away, a little bit further away, stays there, comes back, and ends up in its original location there. Okay, so that's a distance versus time graph. Okay, now we can use the distance versus time graph and calculate all sorts of different things with it. Yeah, so for example, if I wanted to figure out the object's speed that it's moving at, how fast is it moving at this particular rate? You can actually see there between 0 and 1 second, it's moved 2 meters. So that's actually quite fast because between the second and the third, the first and the second second, sorry, it's only moved 1 meter away. So it speeds up here, slows down, stays still, goes back in a slow manner, and then goes back even faster. Yeah, so you can see that speeding up, tapering off, stop, goes back, and then speeds back up back to its original location. Okay, now we can break this up and actually calculate the speed of the object overall. Okay, so I can do that by using this formula, distance over time, and I can calculate how fast it was moving at each particular section. Okay, so let's go with the first second. How fast was it moving there? Well, I can do that by using the distance there divided by the time. Yeah, so speed is equals to distance over time, right? The distance that was moved is between 0 and 2 meters, which is equal to 2 meters, and the time that it takes for it to move that distance was 1 second. So that's 2 meters divided by 1 second, which is 2, I'll write it down here, yeah, which is equal to 2 meters per second. Yeah, that's the speed that the object has moved in the first quadrant. Now, what about the second one? Yeah, I can figure out how fast is it moving in the second quadrant by doing the same thing. Speed is equal to distance over time. Now, the distance in this particular case, though, is only 1 meter. It might seem like 3, but it was already at 2, and then it moves up to 3 in 1 second. So it's only moved 1 meter in 1 second. Right? And so once again, you can calculate that to be 1 meter per second. Yeah. So here it's moving at 2. Here it's moving at 1. It's a flat line here, right? So it would start at 3, ended at 3, and so the speed here will be 0, 1 meter, and then 2 meter. You can see speeding up, slowing down, not moving, speeding up, and speeding up again. Yeah. And you can calculate the speed it moves at each particular section. Okay, and so you can then try and work out what it is there. Yeah, so this is an object that sort of moved up and then made its way back down to its original location. Okay, if we were to look at a speed time graph, however, you might get a slightly different reading there. Okay, so let's take a look at a speed time graph, because speed time graphs are generally a little bit more complicated than your distance time graph there. Okay, so speed time. Okay, same thing. Gonna try my best to, oh, that was a really bad line, but who cares? Okay, 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. In your exam, I would be expecting you guys to use a ruler. Okay, don't do this because that's really bad, but because I'm doing a crash course, I'm not using a ruler. Alright, 1, 2, 3, 4, 5. Okay, 4, 5. Okay, this time we're looking at speed, okay, which is in meters per second, and then you've got time in seconds. Now, one of the key things to note is a speed time graph is pretty much the same as a velocity time graph when it comes to the calculations. Okay, so for the purpose of this, we kind of treat them as the same. So if we give you a velocity time graph, it can be mostly interpreted as speed just because of the similarities between distance and displacement there. Okay, so you can use that to calculate both acceleration and velocity and things like that. Okay, so I'm going to use the same shape, but the same shape doesn't necessarily mean the object's motion is the same. Okay, and I'll explain why that is in a second. Okay, so there's one there, and then 2, and then hold, and then back down. Okay. Okay, so now you've got something slightly different. Okay, let me explain the information that this graph tells us. Okay, so what it's saying is that the object starts at rest, and then it goes from 0 meters per second to 2 meters per second within 1 second. Okay, and then it is still moving further away, but what it's doing is it's actually speeding up to 3 meters per second, right? And it's accelerating to 3 meters per second by the second. It then maintains that speed, so it's still traveling, it's still increasing its distance, but it hasn't sped up. It's maintained the same acceleration, constant motion, zero acceleration, constant motion. And then what it's doing is that it's still covering distance, but it's slowing down and slowing down to an absolute halt. Okay, so a good way to interpret that would be like, imagine if you had a car at the lights, right? And then what the car does is it speeds up and then it slows down again when it gets to the second set of lights. Yeah, and so that's what the car is doing. It speeds up a lot at the start, accelerates, holds its constant motion in the second one, and then slows down and decelerates by the time it reaches the second set of lights. Yeah, obviously not within 5 seconds, but that's the general principle of it. Okay, now this graph tells us a few different information. You can actually calculate, even though you're given just the speed and the time, you can calculate the distance that the object is traveling at, and you can also calculate the acceleration that it is going at certain points along the graph. Okay, and I'll show you how to do that there. Okay, so let's start with figuring out the distance. Right, you can use this formula with the speed and time to calculate distance, and that is this formula up here. Yeah, distance is equal to speed times time. Speed times time here in geometry is actually just the area under the graph. So if I calculate using geometry what the area is under this particular graph, I can calculate how far the object's moved in this particular time frame, which is 1 second. Okay, how do I do that? I use geometry. So this particular shape is a triangle, so distance is equals to base times height divided by 2. Yeah, so the base of this is 1, and then the height is 2, and so you go 2 times 1 divided by 2, which is the formula for calculating a triangle. Okay, this does require you to obviously know your formulas. For example, the next one's a trapezium, so you're gonna have to try and figure out what the formula for a trapezium is. Right, but you can calculate that 2 times 1 divided by 2 for the first second, which is equal to 2 divided by 2, 1 meter. Yeah, so within that first second, the object has traveled 1 meter. Yeah, which kind of makes sense because it goes from 0 and it goes to 2. It's speeding up during that time. It doesn't start off at 2 meters per second. It speeds up at a constant rate to get to 1 meter, right? Now, between the second and third one, however, you've got a slightly different formula that you then have to work out, okay? So what I've got here is a trapezium, which I can work out because the area of a trapezium can be worked out by going height times A plus B divided by 2. Now, if you're really bad at geometry, you're going to probably have to go back and check over this. The alternative is to break this into two shapes and calculate the triangle up there and the rectangle down there. But that's the general principle, okay? What's my height? My height is actually between 1 and 2, which is 1 times A is this one here, which is 2. And B is that one there, which is 3, yeah? 2 plus 3 is 5 divided by 2. So 5 divided by 2 is equal to 2.5 meters. So this midsection here, the object has traveled 2.5 meters, okay? Now, the third one, object has not accelerated, it's not speeding up, it's not slowing down, it's maintaining the same speed of 3 meters per second and then for another second. And so in that particular case, I can then calculate that using a simple rectangular formula. Yeah, so there's my rectangle. So length times width, so 3 times between 2 and 3 is 1. So distance is equals to 3 times 1, which is 3 meters. So that midsection, it's going 3 meters, or it's traveled 3 meters. Now, and that kind of makes sense because if you've got 3 meters per second, yeah, holding that speed for 1 second, it would have only traveled 3 meters in that 1 second, right? So there you've got it. You got 1 there, 2.5 there, 3. Now we're assuming that if it's symmetrical, then that would also be 2.5. I can calculate that, but I'm not going to because I already know it's 2.5, and then that's 1. And so if I want to figure out, well, how far is my car traveled over 5 seconds, I can add the numbers together. 1 plus 2.5 plus 3 plus 2.5 plus 1, right? Which gives me 1, 3.5, 6.5, 8.5, 9, 10. Object has had traveled a total of 10 meters within 5 seconds, okay? And so that gives you my kind of overall distance that the object has traveled during that time, okay? Now, the second thing that the speed time graphs allows me to do is allows me to then calculate the object's acceleration, okay? Now, for the purpose of this one, I'm only going to use this first segment here, which hopefully will be helpful for us to identify how do we figure out its acceleration at each point. Well, acceleration is the velocity or the speed divided by the time. The speed is here and the time there. So the acceleration is actually just the gradient of the graph. The gradient of the graph will tell me what the acceleration is, just like how the gradient of the graph here can give me the speed. By dividing the distance over time, the speed can be calculated through the gradient, the rise over the run. The acceleration can be done in the same way in this particular case. So I can go A, oops, my pen's running out. A equals to speed over time. Yeah, so in the first second, it's from 0 to 2, so that is equal to 2, right? Meters per second over how many seconds? 1 second between there and there. Yeah, so the object goes there, between there and there is 1 second. So the acceleration is actually 2 divided by 1, which is 2 meters per second squared, because that's the unit for acceleration, meters per second squared, not meters per second, okay? So that's my acceleration over the first second, yeah? So that object's acceleration is 2 meters per second squared, okay? I can then calculate the second one between there and there. Now, one of the key things to note is when you're calculating the gradient there, you're not taking the whole number of 3. What you're doing is you're taking the difference between 2 and 3, which is 1. So the acceleration in the second quadrant, or the second segment, is it started off already at 2 meters per second, and then it increases to 3 meters per second. So the difference is 1 meter per second divided by the time it took for it to do that, which is 1 second. Yeah, so that's equals to 1 meter per second squared again, right? Once again, meters per second squared, not meters per second. So you can see that in the first second, the object was actually accelerating. It was going faster, and then it was slowing down again. It's not going as fast. It's still accelerating, but it's accelerating at a slower rate. In the third quadrant, right, right? You can calculate that. Again, it starts at 3, but it finishes at 3. So A is equals to speed over time, which equals to, well, it hasn't actually changed its speed at all. So it's actually 0 divided by 1 second, yeah? Which equals to 0 divided by 1 is 0 meters per second squared. So this time, in the third second, the object has maintained its speed. Now, a zero acceleration does not mean it's not moving. It means it's moving at a constant rate. It's neither speeding up or slowing down, right? And then by the fourth second, it's now slowing down at the same rate as it was in the second second, which is 1 meters per second, and then it's slowing down even faster by that last piece until eventually it stopped moving altogether because the speed has reached 0, right? And so the object has finally stopped moving. Right? So you can see there, this speed time graph is really useful because I can calculate how far the object's traveled in that time, 10 meters, and I can calculate the acceleration it's moving at each particular point, which happens to be 2, and then 1, and then 0, and then 1, and then 2, right? To show that the object is moving, speeding up or slowing down. Okay, so that's distance time graph and speed time graph, and using those graphs to calculate information. Now, one of the key things that you'll need to be able to do is to draw these graphs based on information. So we give you a graph, if we give you a table, for example, and if it was a distance time one, and I say that distance is like that, and I go, right, and for example, it was 0, 0, 2, 1, 3, 2, 3, 3, 2, 4, 1, 5, right? Oh no, that's not 2, 1, 0, right? That table will give you the same as that graph, and you just have to draw the coordinates at each one. 0, 0, 2 and 1, so 2 and then 1, 3 and then 2, 3 and then 3, 2 and then 4, and then 0 and 5. Yeah, so the coordinates of these tables equates to that graph, and you should be able to recognize the table and the graph. It is the same as what you do when you do results in science for experiments. It's the same when you calculate tables and graphs in maths. Okay. All right, so that's that. Next one, we're going to look at acceleration, and then we're going to use these formulas to try and calculate object motion used under different circumstances. Okay. All right, hey guys. So this time we're going to take a look at calculating acceleration, how we're going to work some of those things out, and see if we can try and use the formulas over here to try and work them out. Okay, so the first formula is really looking at change in speed over time. That's what acceleration is. Okay, so acceleration really is looking how an object changes in velocity over time. Don't worry about that, that was my phone. Yeah, and now that change is really important because when we track the change in two different ways. We look at where it started in terms of its speed, and then where it finished, and look at the difference between the starting speed and the final speed. And so that's what these formulas are all kind of investigating and looking at, okay? So A is equal to velocity over time, but what that really looks at is we want to find out what its final speed is, or final velocity, final speed, and we take away from its initial speed, yeah? Yeah, and then we divide all of that by the time. Now, what do I mean by that? Right? Let's say you've got an object that was stationary. It was stopped, it wasn't moving at all, so its initial speed, which we're actually going to call u, right, is 0 meters per second. Yeah, the object is not moving, and so the initial speed is already 0. And then, let's say, after a certain amount of time, it speeds up to a final speed, and it ends up, during the time that we're tracking it, at 10 meters per second, okay? That's easy to figure out because what's the difference in speed? The change in velocity was 10 minus 0. Yeah, you take the final speed and you minus the starting speed that it was at, and you end up with v minus, oops, not v equals, v minus u is equal to 10 minus 0 because it's already stationary, which is equal to 10 meters per second, yeah? And so the change in speed is 10 meters per second. And then if I said, well, let's say it did that in 2 seconds, so t equals to 2 seconds, then I can calculate what my my acceleration is, yeah? So it will be 10 minus 0 divided by 2, which will just be 10 divided by 2, which will be 5 meters per second. Now don't forget the squared, because what we're saying is that it's changing its speed at a rate of 5 meters per second every second, yeah? So after 1 second, it will be moving at 5 meters per second. After 2 seconds, it will be moving at 10 meters per second. 3 seconds, it'll be moving at 15 meters per second, yeah? And so what it's doing is it's speeding up every second. It's going at 5 meters, then 10, and then 15, and so forth and so forth, okay? So that's what the acceleration tracks, okay? Now, that's if the initial speed was going from rest. Not every object is moving at rest. For example, in the previous example, I was telling you guys in the graphs that, you know, if an object was moving at 0 to 1, it was accelerating. But then between 2 and 3, that is the change or difference between its initial and its final velocity. So if we have an example where, say, for example, the object was started off at 20 meters per second, and then at the end when it was tracking it, while we were tracking it, it finished at 15 meters per second, which is really fast, by the way, right? And it did that, let's say, for example, it did that in 4 seconds, right? You've now got a slightly different number that you have to calculate. So you use the formula to calculate the acceleration, right? A equals to v minus u over t. Final velocity was 50 minus 20, because we want to find out what the change was over 4, which will be 30 divided by 4, which will be 7.5 meters per second squared. So you now have the object is moving at 7.5 meters per second every second, yeah? Once again, you can track that. First second will be 7.5, second second would then be 15, third second 22.5 meters per second in terms of their speed, yeah? So that's how you use the formula to calculate these things, yeah? Now, that's what this is, and that's expanding on that, right? And then what we've done is we've just rearranged the formulas so that you can figure out what the final velocity is using the other 3, the initial velocity using the other 3, and then the time using the other 3. So that way, if I give you 3 out of the 4, you'll be able to calculate the last factor in that, and that's what it's all about, right? I might give you the speed, the final speed, the initial speed, and the time, and you calculate acceleration. If I was telling you that the object was moving at an initial speed and then it accelerated over a certain amount of time, then you can calculate the final speed, and then vice versa, and for the others, okay? So that's what we're going to try and do, yeah? So I'm going to give you a scenario, and we're going to split it a few different ways and see how we go there, okay? So let's say a car, let's go with our example, okay? A car was moving at 20 meters per second, yeah, and then it speeds up to 26 meters per second over 13 seconds. Yeah, so there's your scenario. A car was moving 20 meters per second, then speeds up to 26 meters over 13 seconds. What is its acceleration? Yeah, and so I can calculate that. I can go, okay, well, how do I figure this out? Let's use the formula. You have to figure out what the units are, and so the first thing I would do is I would actually write down what would V be, what would U be, what would T be, what would A be, and try and figure out, okay? The question is asking what's the acceleration. So we know that the A is the unknown. That's what we're trying to figure out. Which formula do we use? This one here, because the A is used to calculate the others there. Okay, so let's track. How do we find out what each of the other stuff is? it was moving at 20 meters per second and then it speeds up. So it's telling you that the initial speed, u, is 20 meters per second. It speeds up to 26, so v is therefore 26 meters per second, right? And it does that over 13 seconds, so t is equal to 13 seconds. I now have all my components ready. I got the v, the u, and the t. So I go, I'm going to do it over here. A equals, whoa, did you guys see that? That was crazy. I totally got my whiteboard. Wait. Let's pretend nothing happened there, okay? All right, so A equals to V minus U over T, and V is 26 minus 20, all of that divided by 13, which equals to 6 divided by 13, right? Which will probably be just a little bit over halfway. I can calculate that, hold on. 6 divided by 13 is 0.46, yeah, which equals to 0.46 meters per second squared, right? And so that's my acceleration. It's moving at about 0.5 meter per second every second, okay? That's the first formula, yeah? See how we use the first formula to calculate that one? Let's go with another example, okay? Now for the purpose of this, I'll use the same numbers, but I'll rearrange the question to see if you guys can try and recognize which formula you should be trying to figure out, okay? Okay. If a car accelerates at a rate of 0.46 meters per second squared for 13 seconds, if it started at 20 meters per second, what will be its final speed? Yeah, we're using this formula here to try and figure that out. Okay, v equals to u plus at. Yeah, v is what we're trying to figure out because that's the final speed, right? So we're trying to see if we can identify what u is, a is, and t. Yeah, so u is the same, 20 meters per second. A is equal to 0.46 meters per second squared, and the time was still the same, 13. Yeah, now we use a different formula, however, u plus at. So you can go, okay, 20 plus 0.46 times 13, yeah, which will be 20 plus, was that 6? Yeah, which equals to 26 meters per second. Yeah, and so my final speed is 26 meters per second. Now, these are the same numbers, right? But you can see how a change in the equation, the change in the question requires you to then use a different formula to work it out, right? Now, I can do the same for all of these, and the expectation is that you guys are able to recognize what you are searching for. Is it A? Is it V? Is it U? Is it T? And then you're using the correct formula to then calculate it, okay? If you pick the right formula, I would double check the way that you're working out so that you don't make the mistakes. A lot of people, when they're working this out, will go 26 minus 20 divided by 13 straight into their calculator. And if I do it on calculator, I'm actually going to show you guys what that looks like for people who don't actually watch it. There's my phone. And if I go 26 minus 20 divided by 13, I am not going to get the answer I want because what I've done is I haven't actually put the brackets in correctly. So please make sure that you guys are aware of that. See that answer? That's wrong. 24.46 is incorrect. It is 0.46. And so what you should be doing is you go bracket 20, oh sorry, not 20, 26 minus 20 bracket and then divided by 13, okay, and that'll give me the right answer that I'm after. Okay, so just make sure that you guys don't make that mistake. All right, so that's acceleration. and working out acceleration. If you get a negative number, that means the object is decelerating. Okay, so I'll end with this little, kind of like little final pump, right? Suppose the car started at 26 meters per second, and then it finished with 20 meters per second, yeah? And let's just say t is 13 seconds again. So you've now got a equals to the opposite, yeah? 20 minus 26 divided by 13. Don't just ignore the negative, because the negative matters, right? So the accelerating rate would now be negative 6 over 13, or negative 0.46 meters per second squared. That negative is telling you that the object is actually decelerating. It's slowing down, not speeding up. So the acceleration is negative 0.46 meters per second squared. The object is slowing down its motion, not speeding up its motion. Okay, so that's that. Hopefully this is really helpful for you guys. If not, bad luck. Okay, have fun with your exam.